session. Okay, thank you guys for joining and welcome all of you for the machine learning session from GDSC and our speaker. Thank you very much for joining. So I'm Anuhya. I'm an ML core lead at GDSC UWM. So we have our speaker Kaushik from Dell Technologies. Welcome, Kaushik. Brief background from him is like he's a data scientist with experience in diverse backgrounds such as astrophysics. He's an astrophysicist. He's an industrial and petroleum engineer and then computer science engineer too. So we would like to know what made you go into the machine learning field, what made you interested in that, how you kept your foot in this field, and how you achieved your dreams, and what is your research going on in the machine learning field. So we would like to know all these things in this today. So thanks for taking time from your busy schedule and joining today. So without any delays, let's welcome Kaushik. Kaushik, stage is all yours.
All right. Thank you, Anuhya, for the wonderful introduction. Let me share my screen again. All right. Yeah, I do talk about my background. I know one of the first questions whenever I introduce myself to people is why such diverse background and everything. Yeah, I do talk about it, but yeah, Q&A session, all yours. Any questions you have, you can go into detail. All right, let's get started. So welcome everyone again to the machine learning session today. So I'm Kaushik, as you already know. I'm your speaker for today, and I also want to thank the Google Developer Student Club at the University of Wisconsin-Milwaukee for inviting me to give this seminar. So let's get started. All right, so to give everybody some context on who I am, so as I mentioned, I'm Kaushik. I'm a data scientist at Dell Technologies. I'm also a machine learning visiting researcher at Texas A&M University in College Station, Texas. So obviously, wherever I go, I have to represent my university. So here I am, decked out in fully A&M gear. So a little bit about my education background. I am a PhD candidate. I still am a PhD candidate at Texas A&M in applied machine learning. I'm set to graduate sometime in mid to late 2023, so next year. And the timing depends on how much free time I have outside of my work at Dell Technologies. So I'm kind of dealing with similar stuff as you guys. I'm a full-time data scientist. I'm not a co-op, but still, I'm doing my PhD and my full-time data science work at the same time. So as Anuhya already mentioned, I do have two more master's degrees, one in industrial engineering, also from Texas A&M, which I'll receive in December this year, and a second one in petroleum engineering with a specialization in applied statistics, which I received back in August 2020. I'm also a master's student currently in the computer science department at Georgia Tech in Atlanta, Georgia. So this is something I enrolled in 2021 because, as you can see, most of my machine learning background at Texas A&M was the theoretical aspects of it, the statistics and the mathematical background of it. But my software engineering and software development skills were not at the level that I wanted them to be an effective data scientist. So I figured a computer science degree at Georgia Tech might be a good way to go about it. So I'm a student there. I might finish that degree in maybe 2 or 3 years. At this point, it's just a hobby for me that I do on the weekends. So before all of this, before my graduate journey at Texas A&M, I received a bachelor's degree in astrophysics from Arizona State University in Tempe, Arizona. This was back in May 2017. So that's a little bit of background, my educational background. And now coming into my data science journey and my career progression throughout the past few years within data science. So this is in reverse chronological order. So during and after my bachelor's degree in astrophysics at Arizona State, I was involved in NASA's Mars rover mission. So many of you may have heard, may have seen in the news. In 2020, it was a big deal. Everybody was talking about it. They launched their rover and it landed on Mars. I believe it's still going on. They're still collecting data. So Arizona State has a huge NASA connection. They have a whole school dedicated to this. They call it the School of Earth and Space Exploration. They get a lot of NASA funding. They get a lot of NASA projects. That's how I got involved with the Mars rover mission. I started with them in the fall of 2015. I started as an undergraduate data science intern. And I was working on building a pathfinding algorithm for the prototype rover. So Arizona State, let me be clear, Arizona State did not build the rover. They just built the prototypes. The students started building the prototypes, and then the professors took over, they built on it. And then the actual JPL lab, the Jet Propulsion Lab people took over, and they did the most of the work. We were just, they just gave us a little bit of money and let us play with it for a little bit. So that was the project we had. So after the fall 2015, 2016, I became a data science co-op on the same project, working on the same thing, pathfinding algorithm, optimization, and all that stuff. And after graduation in 2017, I just became a full-time data scientist with them. And I was there until mid to late 2017, August, September. That's when I left the job to come to Texas A&M. I moved to Texas to start my graduate degrees at A&M. And when I got to A&M, I started as a predictive modeling research assistant there in my first semester. And my research for my master's, petroleum engineering master's degree, which was my first one, was focused on machine learning applications for oil and gas drilling automation. So oil and gas, they had a lot of money. The industry as a whole had a lot of money for decades. So they never bothered to actually modernize and use modern techniques and technologies. Even now, many of them still use Excel to do most of this stuff. So they just, when I got to A&M, that was the point where they started feeling the pain of oil prices going down. So they started using new technologies to optimize processes. So drilling automation was one of the big things everyone was focused on at that time, to automate as much of the drilling process, oil and gas drilling process as possible. So I was promoted to a data science research assistant based on changes to my research requirements and a couple of other factors. And after I finished my master's degree in petroleum engineering, so Texas A&M University, just for some context, has a satellite campus in Doha, Qatar. So a few of the professors there were doing a similar project as what I did for my master's. So they saw my work, they saw the papers I published on my master's thesis. They liked the work, so they gave me a fellowship to come and spend time at Doha at the Doha campus and continue my work. So I took the opportunity. I went to Doha in early 2021, and I continued working there. I was a data science lab manager there and a visiting machine learning researcher, which is what I am still to date at Texas A&M. I worked there for a year and a half, but at that point, I felt like I wanted to gain more exposure to practical applications of it outside of oil and gas and outside of academic research. So that's why I applied for internships outside at tech companies and many other companies. And obviously I got the job at Dell Technologies. I interned with them this summer, along with you guys, I guess. Uh, and then I came back as a full-time data scientist. They liked the work I did for my internship project, so they gave me a written offer. So I came back as a full-time data scientist, and I'm working here right now while trying to finish up my PhD. Most of my research is done, so I'm just trying to uh, combine all the papers I published into a thesis and defend and just get done with it. So that's where I am right now. So that's a little bit of background, my education background, my data science journey and everything. I know many of you may have questions about this. So we can talk about this at the end. So this is how the rest of the talk is structured. Most of it is technical. I did not know what the breakdown should be. So I just broke it down into three parts. For the first part, I talk about my PhD machine learning project. So the problem that we tried to solve, the surrounding context, the experimental setup we had, and the data we collected, the ML model building, the data preparation, and all that, the whole thing, and the results and validation of our results. And then for the second part, I talk about the project I worked on at Dell for my internship, and it's the same project that I'm continuing to work on as a full-time data scientist. Unfortunately, because it's an internal confidential project, it's proprietary as well. I cannot go into as much detail for this project as I would for my PhD project, but I'll still try to give some context, what type of data we're using, what are our goals, the business case, the results we're expecting, and all that. And finally, I hope we'll have time for this. I'll go into data science career discussion, a few tips on breaking into data science, and maybe some job search tips that could be useful for everybody. All right, let's get started with the first part of the talk. So my machine learning PhD project, what it is, what we did, what are the results. Okay, so the main problem that I tried to solve for my PhD is called gas kick. So many of you may remember this picture. So this is what happened in the Gulf of Mexico with BP in 2010. So BP, British Petroleum, they were exploring for oil in the Gulf of Mexico back in 2010. They had an accident. Their drilling rig blew up, and the oil started spilling out, and they could not contain it in time. So the oil continued spilling out for 2 or 3 months. So all the 11 crew members unfortunately lost their lives. 4 million barrels of oil, which is a lot, spilled into the Gulf of Mexico over 3 months in 2010. Obviously, this was a disaster. Losses in marine life, damage to the shorelines, fines, loss of natural resources. It was a complete disaster. So this was caused by something called a gas kick. So whenever we're drilling anything below 100 feet, we don't just take a drill pipe and drill. That's not how it works. Because the formation, the rocks and formation that we're drilling into, they already have gases and fluids within them. So if we just drill using a metal pipe, those are going to escape into the hole you're making, and they're going to come out and cause something like this. So to avoid that, we normally, whenever we're drilling below 100 feet, anywhere in the world, offshore, onshore, anywhere on Earth, or even in space, NASA is doing that right now. We always use our own fluid within the hole we're making to maintain pressure and keep the formation fluids where they are until we want them to come out. And whenever a drilling engineer is going about their job, doing all of this, they sometimes accidentally enter a gas cap. A gas cap is the area where most of the rocks have a lot of gas instead of fluids or liquids, water or oil. And if they puncture those without realizing they punctured a gas cap, the gas will start coming into the hole that we are making, and it will start moving up, and it will start expanding because the pressure decreases as you go up. And if they do not realize that they did this in time, the gas will keep on coming in and keep expanding and keep going up. And eventually it will reach the top. And because most of the gas at those depths is methane, which is highly combustible, it will blow up. That's what we call a blowout. That's what this picture is showing. And it will cause an accident like this. And this is not the first time this happened, and this is not the last time this happened. There were many instances like this since 2010, and there were a few high-profile instances like this even before 2010, since the 1980s. So so obviously, from the context that I'm setting up, it's very important not just for the oil and gas industry to solve this problem. It's also important for space exploration, because these days NASA is trying to drill on asteroids. They're trying to mine gold from asteroids. They are trying to drill on exoplanets. So solving this problem is pretty important to many different fields. So a little bit more context on the exact problem that I tried to solve using machine learning. So as I mentioned, gas kick is when gas comes into the drilling hole that we are making. But like I mentioned, we already are using our own liquid in the drill pipe. So it's usually water-based. We call it mud, call it water-based mud, or sometimes it could also be our own oil from outside. So when gas comes in, so this is called two-phase flow because there are two phases flowing: the gas that's coming in from the formation and the liquid that we already have. So the liquid phase and the gas phase, that's why you call it two-phase flow. And depending on how much gas is coming in, it will create many different flow regions, excuse me. So if the amount of gas coming in is very small, it will form small bubbles like the one shown here. These are similar to the bubbles we see in our water bottles. And we call this type of flow two-phase bubbly flow. If the amount of gas coming in is larger, these small bubbles will combine together and form bullet-shaped bubbles like this, called Taylor bubbles. And we call this two-phase slug flow. And if the gas coming in is even larger, these bubbles will grow in size, but because of the increase in pressure, the water will break them down. And it becomes random and chaotic, like the one shown here. And we call this two-phase churn flow. And if there's a lot of gas coming in, the gas will actually take the center stage and it will relegate the liquid to the edges, like the one shown here. And we call this two-phase annular flow. So the bubbly flow and annular flow are the edge cases. They are the extreme cases. And slug and churn are the cases in between. And the diagram shown to the right here. So people have figured out that they can use the liquid velocity and gas velocity and represent these flows on a two-phase space, like the one shown here. So at this combination of liquid and gas velocities in meters per second shown, like the one here, it will be bubbly flow. They call it, there are different versions of bubbly flow, but for our particular case, it doesn't matter. So this is all bubbly flow. And at this combination of liquid and gas velocity, it will be slug flow. So it will be this. And at this combination, it will be churn flow. At this combination, it will be annular flow. Now, you can see that, and our goal is to develop machine learning algorithms, use machine learning models to predict the type of two-phase flow that's in the well whenever we take a gas kick. So we know how much gas through domain knowledge, through drilling engineers' experience and other metrics, they all know how much gas is coming in. And we're trying to use machine learning to predict how much, which of these flow regimes that would create based on the flow rates and other stuff. So we're basically trying to recreate this flow map, but using machine learning. So that was the goal, at least for part of my PhD. So this problem, which is already pretty complex, is made even more complicated because most of the modern wells that we're drilling these days are horizontal wells. Long gone are the days when we just drill vertically and we strike oil and we keep extracting. These days, we have to do a lot of fracking. So most of the wells, 80 to 90% of wells drilled these days, even since 2010, are horizontal wells. And since gas is much lighter than liquid, it always tries to go up. Doesn't matter the orientation of your drill pipe. So the two-phase flow in horizontal pipes is much different from two-phase flow in vertical pipes shown here. So I'm not going to go into discussion again on the different flow regimes for horizontal flow. The only important point to note here is two-phase flow in horizontal pipes is much different from, so the naming scheme is different. So the class labels is different basically for machine learning purposes. So at this point, you might have figured out that this is basically a multi-class classification problem in machine learning. Our classes, different classes are different flow regimes, and our supervising variable is the flow regime. And we have, since this is a two-dimensional space, we figured out a way to represent it in a two-dimensional space. We can just do multi-class classification algorithms on a two-dimensional space with gas and liquid velocities on y and x axis. So that's the machine learning problem that I figured out for this purpose. Give me one moment. All right. So now that we have all that context, we move on to how we collected the data. So there were two sources for our data. One was our own experiments, which is what I will talk about now. And we also collected data from other people's experiments that were published in literature. But first, let's talk about our own experimental data collection. So since we had two cases, vertical two-phase flow and horizontal two-phase flow, obviously we had two different experimental setups. So this one is a vertical two-phase flow setup. This is about 43 meters tall, 141 feet, or that's about 11 floors in a normal Texas A&M building. So the outer pipe shown here, it's made of acrylic and it's 5.5 inches in diameter. Inner pipe is made of metal and that's 238 inches in diameter. And this is the orientation we used because probably need to go back. This is the orientation we used because in this diagram, the gray cylinder represents the drill pipe we are using to drill, and the outer boundaries represent the actual hole we're making. That's why this is a tube inside a tube setup to accurately represent that type of setup. So the outer acrylic pipe is supposed to be the hole that we are making, and the inner pipe is supposed to be the drill pipe that you're using to drill. And we call this type of space annular space because there are pipe inside a pipe. And the orientation of this setup, it's completely vertical because it's 11 floors tall. There's a lot of setup. It's completely static. We can't move it. We can't incline it. So that's the experimental setup. We filled the whole 141 feet with water and then injected gas at the bottom at different flow rates at different velocities to see what type of flow regime we're getting. Is it slug flow, bubbly flow, like the ones I discussed before? And we recorded the data. So that's our experimental data. It took me 5 minutes to explain the whole thing, but it took us 2 years to actually build the lab and do the and even 1 more year to actually collect the data. So that was a lot of work. And then So this is the experimental setup in Qatar. So that's why they wanted me there. So this one is, as you can see, is horizontal. This is for horizontal two-phase flow. The second case. But the cool thing with this one was this was also inclinable. So we could incline it to up to, I believe, 15 degrees. So we could go from 15 to 14 to all the way to 0, completely horizontal. Uh, I'm not going to bore you with all the stuff. This is slightly smaller. This is only 20 feet long. Uh, Maybe it's like a room width. And this is so schematics and dimensions. You don't need to know all those. So these are the two experimental setups, one for collecting vertical two-phase flow data, one for collecting horizontal two-phase flow data. So now coming to the part that you are actually interested in, using machine learning for two-phase flow classification. So data collection and cleaning. So like I mentioned, we have our own experimental data, but we also collected data from open literature. So people have been doing two-phase flow experiments, maybe not horizontal, but vertical two-phase flow experiments. People have been doing it since the 1970s. So there is already a lot of literature, but not many people use machine learning to actually generate flow regions from that data. They just use traditional two-phase flow modeling and some other techniques to develop their two-phase flow maps. The two maps that I showed before, those were developed using traditional modeling and traditional methods. So initially, these should be updated. Right now, we have a lot more data, but initially we worked with 3,500 data points that we collected from open literature, which is quite small, but we just wanted to show like a proof of concept, and 1,000 data points from our experiments. We had a lot more, but we had to weed out a lot of duplicate data. So we settled at 1,000 data points from our flow loops. So the main features for our machine learning models, like the ones we discussed, were gas and liquid. So we call it superficial velocities. They're not the actual velocities, but it's based on domain knowledge. You don't need to know what superficial velocities means, but those are the two main features because we're creating a two-dimensional flow regime map. We also had to do log transformation on our data because a few large values were skewing the visualization. So we had to log transform to actually see the flow regimes within our data. And we wanted to keep it simple. So we just use box plots to detect and eliminate our outliers. So this is for vertical two-phase flow. So this is data pre-processing, vertical two-phase flow. So the graph to the left shows the raw data and log transform. So these are not absolute numbers. These are exponents of 10. So this is 10 to the minus 2, 10 to the minus 10, and so minus 1, and so on. Similarly here. So this is liquid superficial velocity, gas superficial velocity, and this is the raw data and the different flow regions for vertical two-phase flow, and they are shown here. There are a lot more here than the 4 that I discussed, because since the 1970s, people have been coming up with their own minor flow regions that are transitions between the major flow regions, the 4 major flow regions that I discussed. But for our scenario, we didn't care about the minor ones. We are just trying to figure out 4 or 5 major flow regions. So the graph to the left is pre-truncation, so before we eliminated any outliers, and the one to the right is after we eliminated the outliers. You can see the difference here. These are the ones we identified as outliers and eliminated them to do our machine learning modeling. Similarly, for horizontal flow, pre-truncation, post-truncation, and obviously the flow regimes are different here, like we discussed before. So we did use initially, we used two machine learning models, supervised machine learning models, and 2 unsupervised machine learning models. But since then, we expanded and went into, so the initial 2 supervised models we used were k-nearest neighbors and support vector machines. But since then, I expanded also to use tree models to see how they perform. But for this presentation, I'm only going to talk about k-nearest neighbors and SVM. Obviously, this slide just talks about how the KNN model works. I had to add this slide for my other presentations because I'm presenting to petroleum engineers. Most of them don't have a background in machine learning, but I'm not going to go into the details here because most of you probably already know how KNN works. So jumping straight into the results. So this is the flow regime map we generated using KNN with a K value of 37. So we are considering 37 nearest neighbors to achieve this flow regime map. So as you can see, it identified 5 different major flow regimes. Like I mentioned, it did have a lot of minor ones, but for our purposes, we did not really care about any other minor ones. So the major ones, like I discussed at the beginning of the presentation, is bubbly flow, slug flow, churn flow, annular flow. And we had, because of the new data labeling, we also had a new one called intermittent flow, which is kind of similar to bubbly flow, but we don't need to talk about that. And similar map for horizontal two-phase flow. Again, we had 6 distinct flow regimes. These are the 6 new ones for horizontal two-phase flow. But an interesting thing you'll notice, which we will talk again at the end of part 1, is this one actually matches up quite nicely with the flow regimes that other people have proposed before, the one we saw at the beginning. So that's kind of a validation for our study, but we'll get into discussing that when we actually go into the results and results validation. Sorry. And the other supervised model we used initially was support vector machines. It also performed almost as well as k-nearest neighbors. We also go into the actual metrics and performance at the end. However, as you know, SVM takes much longer to run and it's much more complicated than KNN. So we just concluded that KNN is the best way to go about it because it runs much faster and it gave really good results for us. So I'm not going to talk about SVM and show the results. Going to unsupervised machine learning, we use k-means clustering and hierarchical clustering initially to do the same thing. So the same data, but now we ignore the labels and try to cluster and come up with our own labels and see if they match up with. This was just an exercise I wasn't really expecting. The only expectation I had, which was a long start, was maybe clustering would be able to, unsupervised learning would be able to identify some new flow regimes that weren't there before, or maybe they can identify new flow regimes in actual real world situations. That was the only expectation. Otherwise, this was just an exercise to see how they match up. So this slide just talks about the k-means clustering algorithm. So I'm going to skip over this to save time. These are the results from the k-means clustering algorithm, same data, but a k value of 6. So we're basically telling the algorithm to come up with 6 clusters and optimize to 6 clusters. So they could correspond to 6 major flow regions. The ones KNN showed us, the ones other people have showed us. But the interpretation is subjective, like I mentioned, because we're ignoring the labels and doing our own clustering. So we can say, okay, this is bubbly, this is slug, but it's subjective. It's in the eye of the beholder. But the optimal number of clusters was between 10 and 15, which actually makes sense because if you remember from the initial raw data plots, there were about 14 or 15 different, including the minor flow regions, there are 14 to 15 different flow regions. So obviously the clustering algorithm also identified between 10 and 15 as the optimal number of clusters. And like I mentioned, this could be potentially useful in novel situations and see maybe a new cluster pops up. Maybe we can say, oh, hey, we're into a new situation that we never seen before, and maybe be more careful. But other than that, the practical application of this is almost non-existent. Similarly, k-means clustering, horizontal with k value of 6. Optimal clusters was between 13 and 16. So since we gave a k value of 6, it will obviously come up with 6 clusters and 6 major flow regions. Again, potential usefulness, maybe in novel situations, but other than that, almost non-existent. Hierarchical clustering, this is a little bit of context on hierarchical clustering, which I'm going to skip over. A key difference between k-means clustering and hierarchical clustering, as you may know, is, first of all, we don't need to specify the number of clusters beforehand. We cut the dendrogram at the end, which will give us the number of clusters. And then we determine what height of the dendrogram to cut at to determine the number of clusters we're going to end up with. And another major difference, hierarchical clustering actually allows overlapping clusters, unlike k-means clustering. And we use linkage method to measure the dissimilarity between different clusters, between observations between different clusters in hierarchical clustering. And depending on which linkage method we use, the results could be quite different. And quite different, I mean, the cluster size in k-means clustering should be roughly equal for all the clusters. It doesn't matter how many, what k value you give it. But that's not the case with hierarchical. Depending on which linkage method you use, there could be lopsided clusters, which is what you'll see in the results. So this is for vertical two-phase flow hierarchical clustering results. So you can see the lopsided, imbalanced clusters. Again, I cut the dendrogram so that it gives 6 clusters. So they could correspond to 6 major flow regions, although it's doubtful because these can't be bubbly flow because bubbly flow, as we saw from the maps, is quite large. Everything else is similar too. So the optimal number of clusters again is 10 and 15. Again, makes sense because that's what we had in the actual data. If we do consider the labels, potentially useful in novel situations, just like k-means clustering. Same thing, but horizontal two-phase flow, lopsided. You can then clearly see the overlapped clusters. Now, coming to results validation. So since we, at least for initially for this part of the study, since we concluded that KNN is the best one to use because of the speed and also the performance, we compared the results, the visualization we got from KNN with a well-accepted two-phase flow map that is already in literature. This is what petroleum engineers use today. This was developed using traditional methods, normal two-phase flow modeling. So you can see there is a huge, they almost match up perfectly. So you can see the bubbly region. So this is the, just clubbing the dispersed bubbly with bubbly, you can see the bubbly region, and then the slug flow region, and then the small churn flow region, like the one here, and then the annular region. So they did not have any intermittent flow data in their data sets, but we did. So that's why we have an additional one. And we also have the many the minor regions. This was from back in 1992. So people have proposed a lot more since then, like I mentioned, that's why we have so many more. So this kind of served as validation for our study. So this shows that, okay, now we can develop a machine learning module that can predict a two-phase flow within any structure with reasonable accuracy that matches an existing well-accepted flow regime map. Similarly, for horizontal one, this doesn't match up as well, but it still has the similar stratified flow, similar structure, the wave flow, and so on. But the minor flow regions here are much more noisy. I could eliminate the minor flow regions. Let's say if I go to k value of 100, it will probably eliminate most of the minor regions, and it will give a nice graph. But that wasn't. So there are a bunch of rules on how to select the k value that I included in the KNN discussion, but around 50 was the ideal k value. So that's why I stuck with this one, even though it looks messy. All right. So that was part of my PhD research. A few conclusions we made. So we collected around 5,000 data sets, although we have a lot more now from our own original experiments and 60 different studies. We used 2 supervised machine learning algorithms, KNN and multi-class SVM, and 2 unsupervised, k-means and hierarchical clustering. So best performance, KNN was the best one, but SVM also performed similarly. It was only slightly lower than KNN, but we chose KNN because it was very fast compared to SVM. Unsupervised algorithms, we concluded that their practical applicability is almost non-existent, except for novel situations where they might pop up, come up with a new cluster and tell us that we're experiencing a new situation that we haven't seen before. So a few limitations. So because of the limited data we had, I didn't see a point in going to deep learning. So maybe now that we have a lot more data, maybe I'll go into deep learning now. And we are expanding into tree methods, and I expect tree methods to perform as well, if not better than KNN, especially gradient boost. But I'm working on that right now, which is what I don't have time for because I'm working at Dell. We want to repeat this with deep learning algorithms, like I mentioned, because we have a lot more data now, tree methods, bagging, boosting, random forest, and everything. So more training, since we have more training data now, the models will be more robust because we're training on more diverse data sets. And like I mentioned, we are missing a dispersed bubbly flow like we have seen in the flow maps. We want to add those data points into our data and also have that just to make our results more robust. All right, that's the end of part one. That was a part of my maybe a 30% of my PhD research. If you have any questions about this part, we can go about it now, and then I'll start part two.
Hey, Kaushik,
Yes.
I have a question. Great work that you have done. It's really interesting. Lots of technological stuff that you've worked with in machine learning. I just have one doubt. Like, do you think? I mean, I'm not sure if you implemented it in your project, but do you think there's an efficient way of finding the optimal k value when you implement KNN, or is it just like a
Yes. Yes. That's the part I skipped over.
Mhm.
This is k-means clustering. So the rule of thumb is usually you start with an odd number because I mean there is a way to obviously let's say if you're dealing with a binary case and you're using an even value, you could be in a situation where you have to break ties. So usually rule of thumb, start with a odd value and start at a square root of n. So if you have 1,000 data points, start at square root of 1,000 as your k value. And the way to select the optimal k value, that would be, so you obviously look at the metrics. What is your precision? This is a multi-class problem, and it was also an imbalanced data set. So you have to look at the precision recall F1 score for each separate class that you have. And obviously, you also know if you have a very small k value, you will overfit. This is actually, I talk about this in the paper we published. I do show results with the k value of 5, 10, 25, 50, and 100. So the more you increase the k value, the smoother the boundaries become. So the boundaries will become smoother. The smaller flow regions start to disappear. But you are oversimplifying a lot if you increase the k value a lot, too much. But if you decrease the k value too much, if it's too small, you are overfitting the data, there's too much noise. I mean, this is not even the worst case. If you go down to maybe 10 or 15, this looks much worse. So your k value shouldn't be too large, definitely not closer to the number of observations you have, and it shouldn't be too small. So rule of thumb, and then use the maybe plot your test error with the k value. Usually, if you did it right, it will be U-shaped. It'll bottom out at some k value, maybe like between 40 and 50, and you say, okay, 45 is the best one from my U-shaped curve between error rate and k value.
Thanks, Kaushik.
Yeah.
Okay, any more
Please
questions
post
on?
your questions in the chat if you want me to ask Kaushik, or you can unmute yourself and ask questions to Kaushik. Okay, I don't see any questions in the chat.
Okay.
So let's proceed further, Kaushik.
And cleaning, so if any of you have limited experience dealing with messy data, ours was quite clean already. So that's why we just had to do outlier detection, but that's not how usually data works. You have a lot of missing values, you have outliers, you have format errors. I don't talk about all this because so to save time, first of all, and we also had a lot of clean data. So don't get it twisted. You're gonna, most of your work is gonna be maybe 30%, 40% is gonna be cleaning your data and preparing it before you actually build your models. And box plots will not always work. We had a simple use case and we wanted to keep it simple. That's why you use box plots. There are other methods. KNN is actually one of the methods you can use to identify outliers and eliminate them. Just to give you all some context, it's not this easy always. This is a research project, so we can make it easy. All right, end of part one. So there are no questions. Now let's move. What time is it? How much time do I have left?
You have 20
20
minutes.
minutes. Oh yeah, should be good enough. All right, now moving on to my project I did at Dell. Okay, so just to give everybody some context. So the Dell support website, just the support website, not the product pages, gets millions of visits every week. Not all of them unique. There are repeat customers, repeat people coming back to solve different issues, but millions every week, even if you eliminate the repeat customers. So we obviously have the browsing logs for all of those visits. And we also occasionally send out surveys to a few of these users to get their feedback on the ease of navigating the Dell support website and the ease of finding relevant information. We obviously have the response data for all these surveys we send out. A few of these users, for a multitude of reasons, eventually go on to contact a customer support agent to resolve their issues. So we have the call data for all these customer support calls. So my project for the summer and the one I'm working on right now is to leverage all these data sets. So the browsing logs, the survey data, the customer support call data, and build an intent prediction model that predicts why someone is on the Dell support website without them actually saying anything. So we want to proactively predict why they are there before they type anything, search anything, or contact a customer support agent to say anything. So this intent prediction model is important because it is a critical first step in building an effective recommendation engine. So any recommendation engine will use the predictions made by the intent prediction model to generate their recommendations, be it product recommendations, article recommendations, or video recommendations. But why are these recommendations important? Why is effective recommendation important? It's important because effective recommendations lead to streamlined customer journeys because users are not bouncing around as much and they're not clicking on as many things to find what they need to find to resolve their issues. So streamlined customer journeys means faster issue resolution because obviously they're not spending as much time to resolve their issues. Faster issue resolution could mean less frustrated customers and higher customer satisfaction, which is an important metrics for Dell, and not just for Dell. Customer satisfaction is an important metric for any company that cares about their customers at least. And faster issue resolution could also mean reduced number of support calls, which saves us man hours in the actual support that they're providing to the customers, and it also saves us money. So that's why, so these are the metrics we're trying to improve. So this is the data we have. I can't go into the models we use, although I forgot to delete these, but I cannot go into the details about the models we use because it's proprietary. So this is the context. This is the project I did in the summer that I'm continuing to do and where it fits in within the objectives for our team and within the bigger picture for Dell. So since I'm not going to be able to talk about the models we use and the data types we use, but I can show you example results that we got. So user one, they came in and our model takes in inputs. One of the inputs is a persona. So persona is something we developed internally. So based on the amount of time a user is spending on different pages of the support website, we classify them into one of many personas. So persona, they are labeled as learner. Learner are people who are spending a lot of time reading articles. Buyers are people who are spending a lot of time browsing the product and accessory space. So they're likely trying to buy something. And then we have also solver persona, which means they're running a lot of diagnostic tests on the support website and they're downloading drivers and doing whatever other trying to solve something. And so on, we have many other personas based on their activity. So that's one of the inputs for my model. So the other inputs are the age of the system. User one is more than 2 years old. What country they are coming from. I know people are using VPNs. This is not reliable, but this is what we got. This is what we have to work with. But so country they're coming from, the US. Warranty status of the system. So you probably already dealt with your computer company about this. If you're out of warranty, you're probably not gonna reach to a customer support agent in time. So warranty status, customer type. So are they enterprise user? So are they a company? Are they consumer? Are they individual user? Or are they, so three types, consumer, commercial, and enterprise. Commercial users are also companies, but it could also be individual users. And system type. So this is the Dell computer that you're using. Are you using an Alienware laptop, a Vastro, XPS, a desktop, server, and so on. So the model will take all these inputs. And for this user one, my model is predicting that they're likely, based on all these, they're likely trying to solve a battery issue. How that's doing, that's within my clustering and XGBoost model. So user two, their buyer's persona, their computer is very old, more than 4 to 5 years old. They're also coming from the US, out of warranty. They're a commercial user, and they're using either a Latitude or an Optiplex desktop. So and based on these inputs, my model is predicting that they're likely running out of storage, and they're trying to solve that by either buying external storage or buying additional storage. So those are the immediate, I call them immediate intents because I'm predicting what they're immediately trying to do. So that's what I did for my internship. But for what I'm doing right now is to extrapolate from these and see why they're trying to solve these issues, and try to use maybe telemetry data and other data we have available to get to a point where I can actually say, okay, this person is running out of storage because they installed a bunch of games on their computer and they're trying to game. So I call that high level intent. So my model right now is able to predict the immediate intents based on their activity, but we want to get to a point where we actually predict why they are trying to do that. And another example I give everybody is, if somebody is on the website and they're trying to download graphic drivers and they're trying to buy maybe a GPU, maybe they are trying to game if they're using, let's say, Alienware, or maybe they are a data scientist running a lot of deep learning models. We don't know. So that's where we want to get to. We want to know exactly what they're doing. So that's my project. Unfortunately, I can't share any more about that, but if you have questions, I'm happy to answer. So this is end of part 2.
Yeah, Kaushik, I have a single question. You told like you are using support the call data.
Yeah.
So is the call data and the audio files you are using unstructured data, or it's also like any log files or something?
No. For now, it's just chat logs.
Okay.
We are not into audio yet, but I am going into NLP. I'm trying to get into NLP to see if we can find patterns within users. But yeah, we might get into that at some point, maybe not immediately.
Okay.
It's just chat logs, search logs, survey data. Survey data is this is the simplest one we have. So they just fill out surveys. We just have on a scale of 5. This is the messiest one we have. And the actual support agent who takes the call, they take a lot of notes. So we can use NLP to extract keywords from it and see, get a bunch of insights.
So you can say like support call data is a totally a total data which you needs cleanup a lot.
No. Yeah. Because the
Okay.
browsing logs is the
Share some
messiest
data
thing.
about like how you are cleaning them, if possible?
The support call data,
Yeah.
how we are cleaning the support call data. I'm
Or
trying
any
to.
techniques of how you are cleaning the data.
Okay. Forget about support call data. I can talk about the browsing logs, because how it comes in is it just comes in as a bunch of numbers. So it just says prop. The columns are just called prop 1 to prop 20. And we figured out that, okay, prop 1. So I can't tell you exactly what it means, but we figured out that prop 20 means what page they are on. Prop 5 means what computer they are on, and so on. So we had to figure out which one means what based on how the website is structured, and then manually map them. So this is probably not cleaning part of it, but processing. Because if we don't map them, all the props to what they exactly means, there's nothing we can do with it. Nobody understands what prop 1 means or prop 20 means.
Yeah.
That's one thing. Obviously, missing values, we just interpolate most of the time. So that's one of the things. If a country value is missing, like the example I mentioned, let's say we don't have where they're coming from and we interpolate it, is that really reliable? Maybe they're from China, but we interpolate, let's say we have most of our users in USA, and it'll be interpolated at USA. Is that really reliable? Probably not, but that's the best we got. So that's what we're using for now. And formats, most of them come in as strings, even numbers come in as strings. So we have to obviously go and figure out if we can just convert the whole column into from string into numbers. If that's not possible, because a few of them have different properties, we have to deal with that. But that's more of a data engineering job. I mean, even if I was a data engineer, I wouldn't do it anyway because I started like 6 months ago here. But yeah, data engineers do that. They take care of most. So most companies, the most big companies at least, have 3 teams within data teams: engineering team, the science team, and the ML engineering, or the deployment team, the IT part of it. So the scientists only worry about I mean, they do a lot of cleaning and they do build SQL pipelines, but most of their work is focused on model building and converting them into insights. And data analytics team helps with that. But the engineers, they take care of most of the building the pipelines, cleaning. Uh, so their job is to get the data. Obviously, you're doing it. Most of you are probably doing data engineering internships, so you already know your job is to make the data useful to the data scientists as
Yeah.
much as possible. You're not going to be 100%. Most of the
Yeah.
time, data scientists also have to do their own cleaning and messing with the data, but that's your job, data engineers.
Yeah. Thank you. Thank you for answering that question.
Hi there, Kaushik.
Hey, hi.
Can you hear me?
Yes.
Thank you so much. Actually, I never thought like how can we integrate the data science part in the customer service experience, but
Yeah.
this is a very great experience that I have. So one question I have is like, because for me as a web developer or as a DevOps guy, so how hard is it to track an anonymous user? Because whenever we search for these kind of things, we generally don't want to log in into stuff and we just
Yes.
want to get the
Yes.
answer. So when an anonymous user come, because these fields will get emptied out and it's hard to give a prediction for them.
Yeah.
So what kind of strategy you apply for those kind of things?
Yeah, that's actually so at Dell, we never had any recommendation engines before. We did not personalize journeys before. So that's a big thing that's going on right now. So personalization across all formats, product pages, support pages, that's a big thing going on.
Mm-hmm.
Unauthenticated users, we call them, or anonymous users, so like you said, is
Mm-hmm.
one of the big problems that we're facing.
Mm-hmm.
So yeah, if we are using and a completely anonymous. So there are unauthenticated users that
Mm-hmm.
didn't log in, but we still know because of the website cookies. We
Mm-hmm.
still know the computer they're
Mm-hmm.
using, country, likely if they didn't clear cookies.
Mm-hmm.
But they're completely anonymous users. We don't know anything. Maybe they have a new laptop or something. What
Mm-hmm.
we're trying to do, we don't have an answer yet, but
Mm-hmm.
what we're planning to do is you use telemetry data for those
Mm-hmm.
types of users. Telemetry data is something, if
Mm-hmm.
you're using a Dell computer, we know what your computer status is. What is your audio driver
Mm-hmm.
doing? Is it
Mm-hmm.
in good health? What is your video driver, graphics driver, your health information basically.
Mm-hmm.
So we collect that remotely. So it's
Mm-hmm.
not always sent in
Mm-hmm.
real time. The computer has the information,
Mm-hmm.
and if you log in and we determine that you're completely anonymous, we'll
Mm-hmm.
okay, let's get the telemetry data and see if we can use that to uh, maybe predict what they're trying to do. But that's the best shot we have. We don't know if it will work. We're trying to see if it will work.
Mm-hmm. I mean, generally, as you said, telemetry data. So is it not like, do we ask user before itself, hey, we are pulling this information
No.
from your system? No.
So telemetry data, every time you log onto the support website,
Mm-hmm.
just to also uh, help the customer,
Mm-hmm.
we always see the health data of different drivers, different hardware, as much as we can. Uh,
Mm-hmm.
until now, we used to use that to
Mm-hmm.
just see what the health is and recommend. Maybe they need to have a new part dispatch, or just to make it easier for them. But now
Mm-hmm.
we're trying to see if we can use that for our customer support purposes as well.
Okay.
But
So.
yeah, it's a thin line between spying on them and not spying and just getting useful
Yeah.
information from them.
Mm,
But yeah, telemetry data, it doesn't have their personal information. It's just the computer, the health
mm.
status of the computer. So that shouldn't be a problem.
But we can tie that to an anonymous user saying that, okay, fine, user XYZ
Yeah.
has this telemetry data, but we cannot personally identify them then.
Yeah.
Okay. So going on ahead, so Dell is thinking to forcing users to log in before itself using their website so that they can better serve them or something like that.
No, we
No,
don't want to
nothing.
do that.
Okay.
That actually, I would just go back and I'll just go to Reddit or something or Stack Exchange. Uh,
Hmm,
No. So we will ask you to enter your service tag. So service tag identifies the computer type it is.
hmm,
So is it
hmm,
a Alienware? Is it
hmm,
a XPS Precision?
hmm,
Once we have that, we're good. We don't need anything more. We don't need their names, their personal information, anything.
hmm,
Once we have the service tag, we know the system type. We have most of this,
hmm, hmm,
and we can work from there. But
hmm,
if they don't want to enter service tag,
hmm.
again, we'll go back to cookies. But yeah,
Okay.
we would obviously like
Hmm,
people to create accounts and log
hmm,
in every time they come on, but
hmm.
no, nobody wants to do that. Uh,
So I guess, do you believe that whatever Apple is doing in the websites, like forcing users to log in using the Apple ID or giving, letting the model number know beforehand to give them support itself. So is it a better service experience giving to the people, or what do you think on that? Because they are giving, they're doing for a long time, around 5 to 6 years like that.
Yeah, but they
Mhm.
have that they have that luxury because they have other services
Uh-huh.
where you have to create the account and use it. So they already know you already have an account, very likely. So
Okay.
they can force you to log in. But
Mhm.
we just make computers and servers. We don't have iPhones or any
Mhm.
software services.
Mhm.
So we probably don't have that much power to force people to do it. And I personally, if I personally would prefer not logging in.
Yeah.
Uh, I just always clear my cookies. I don't want anybody tracking me, but
Exactly.
it's personal preference. Some people might say, hey, just
Mm,
give me the exact solution. If it
mm,
needs a part replacement,
mm,
don't make me call anybody. Just send me the part. We are done. I'm
mm,
happy with that, even if you want to spy on me.
mm.
It depends
I
on individual preference.
I can truly relate to that, because as a web developer, I would really wish that users can log in so that I can track from my
Yeah,
server side
yeah,
what's happening and all, so that it's easier for me what's going on. But as a user, I don't want to log in.
yeah.
I don't want to get track. So it's a kind of double-edged sword we have to play at the end.
Yep.
So yeah, thank you so much. Actually, that's a very great insight to have. Yeah.
All right. Do we have more questions?
I don't see any questions in chat, so I think we can move on.
Okay, give me one moment. Okay, the final third part of it, we have 3 minutes. Yeah, I'll try to get it done if possible in 3 to 5 minutes. So end of part three. So some career advice, I guess, although I'm not sure how useful that will be to you guys, but here we go. So breaking into data science. And one of the big mistakes I've seen a lot of people reach out to me almost every week, uh, looking for advice and stuff. One of the big mistakes I see people making is they try to apply to every role in the data field, data analyst, science, ML engineer, data engineer. It doesn't work that way. Although there is a lot of overlap, they're completely different roles. They need different skill sets, different tools. If you're trying to just cast a wide net, you're not going to find anything. You have to focus on at least one, maybe two. Data analyst, data scientist makes the most sense. But if you're a data engineer and you're also trying to do a data analyst role, you have to show a lot of relevant background if you want to pull that off. So focus on one role, and tailor your resume to that one role, and optimize your LinkedIn. Always try to get professional help. There are a lot of good professional resume writers and LinkedIn optimizers out there. Most of them cost like $200, which is nothing compared to the stress you will go through if you don't find a job in time. So don't be afraid to invest and optimize your resume on LinkedIn. And projects, most of you seems like already have your own internships, so you're already good. But if you don't have an internship experience and don't have prior data science work experience, always try to find projects that are relevant. Uh, so like if you try to find an industry that's interesting to you, and then try to find projects within that industry. Let's say healthcare, try to work with healthcare data, or if you're interested in the tech sector, try to find that data in that sector. There, you can use your course projects. I assume most of your courses have a project component, so you can use those to build your projects. Academic research positions are a good way to go about it. Just reach out to a professor in a statistics department or industrial department, see if they're looking for maybe even unpaid research intern role. Go work there just to build your profile. Always open source data is always a good source. Kaggle competitions. But more important than doing the projects, visibility is the most important part of it because there are thousands of people doing what you're doing. If you're not visible, you're probably not going to get a lot of responses from applications that you send out. So a great way to increase your visibility, have a Tableau profile. I don't believe Power BI has a public profile like Tableau does. You can build dashboards and add it to your public profile. Everybody can see it. Okay, what data did you use? What dashboards did you use? What insights did you extract from them? What are the results? Everybody can see it. That's a good way to increase your visibility. Also showcase. You can add hyperlinks on your resume to all the projects. Yeah, just similarly in GitHub as well. You can have all your code repositories and add hyperlinks to your uh, on your resume to each of those projects. And GitHub is really important because I just had two interviews, one from Google and another one I believe was from Micron Technologies. Both of them specifically looked at my GitHub because it was on my resume, and they specifically mentioned it to me in during the interview. They're like, "Hey, we looked at your GitHub, this so-and-so repository. This seems interesting to me. Can you talk more about this?" Two times, not just once, within like last 6 months, I would say. Google was pretty recent. It was the last 2 or 3 weeks. So always have GitHub repositories. You don't have to do it in a day or two or even a week or two. Just upload one code file every day or every week. Within a year, you'll have a massive repository, like 52 different code files on there. And always add them on hyperlinks on your resume as well. Similar LinkedIn, add LinkedIn on your resume. Obviously, you're all already probably doing that. So skills to acquire, I can't speak about data engineering or any others, but data scientists, you need to have at least these three for big data, PySpark or Hadoop or any Spark language, SQL and Python. If you don't have these three, don't apply to data science. You're not going to get it. Even if you get in, you're going to struggle if you don't know a big data language, SQL and Python. If you have more time, you can learn R and Julia. Julia is the future. So you can do that. And SAS was the past. It's dead, but some healthcare industries still use it. So it might be a good tool to have if you want to learn more. And visualization tools, you must know at least one. I recommend Power BI because most companies use Microsoft anyway for most other things. So just using Power BI is just an additional extension, but either one works. And machine learning, so obviously supervised, unsupervised, deep and reinforcement learning. And during your interviews, since most of you are computer scientists, be prepared to answer the inner working of the models, not just how to run them. Why exactly, like the KNN, that question you asked, how do you choose K and why would KNN perform better than SVM or SVM perform better than trees? Learn the inner workings of the machine learning models, not just running them and getting metrics. Specializations, you don't need to be have a specialization in an NLP or CV to get a data science job. But if you want to, if you're interested in maybe let's say time series, you can always go and specialize in that. There are a bunch of roles for each one of those specializations. How much time do I have? 3, 2. Just give me one more minute. I guess I'll just run through everything.
Yeah, you can take your time. That's what.
So just a few job search tips. If you're looking for a entry-level role and you're sending online applications anonymously without reaching out to people, the maximum response rate you can expect is 20%. Doesn't matter if you're from Stanford Computer Science, you're from Texas A&M, you're from Wisconsin, doesn't matter. The maximum you can hope for if you're for entry-level roles, completely online anonymous applications, you're not going to get more than that. A way to improve that is to connect with decision makers on LinkedIn, not recruiters. Recruiters are just recruiters. They're just reaching out. Connect to managers, data science managers, data science directors, or just data scientists that you would be working with if you had a job. And try to build a relationship with them. Don't just, I get maybe 10 messages every week, maybe 20. Somebody just randomly reaches out, says, hey, I'm interested in this role at Dell. Can you refer me? No, I can't. I don't know you. Why would I refer you? You have to build a relationship with them before you actually ask for anything. Try to learn about them, what they do, what the team does. And if that's interesting to you, which is an important aspect as well, not if they are interested in you, that's not the only important part. Are you interested in working in that type of thing? Do you want to work in recommendation engines if you want to join my team? Do you want to work in time series? So learn about them. And then after building a relationship, then they will be more willing to help you. And they will probably ask you, hey, we have a role opening up. Do you want to join us? This is I already mentioned this, narrow your industries. Don't just apply to any industry. Quality over quantity, basically. Narrow your search to 2 to 3 industries you're interested in, maybe defense, healthcare, tech, and focus on those. Focus your projects on those industries. Get data in those industries, build your projects and portfolios in those industries related to there. And then you will see that response rate increases if you do that. So a few tips on interviews and assessments. Whenever you're talking about projects or any other experience during an interview, always focus on the business results that you were able to deliver, the practical applications, and what insights did you get. Most people, even after you become a data scientist, most people don't care about the exact models you built, how accurate was it, that you improved the accuracy by 1%. They're important to add on there, but that's not the most important thing. The most important thing is what business results did you deliver? Why is it practical? Why does anybody care about that project? That's the most important thing. So obviously assessments, do SQL and Python, HackerRank, LeetCode. You should be good. You're a computer scientist. You should be good with the coding part of it anyway. Machine learning, as I mentioned, learn the inner workings of the models, not just models. Why something would work, why that would be better than the others, why some metrics might be skewed, and all those things. Behavioral questions, just star methods, is pretty standard. There are a bunch of lists online that you can use. Networking tips, all these career portals, you should have an all-star profile. All-star profile meaning you should have every field filled up on LinkedIn, on WayUp, on Tapped, your university career portal, and Indeed. You should have a complete profile that's descriptive on all of these to maximize your chances, basically. You never know which recruiter might be using which one and where they might reach out. Finally, attend events. Doesn't matter if you feel, it feels like nothing is working out. It always feels like it's a waste of time, but it's not. You never know which recruiter where might like your profile. So always attend on-campus events, conferences, mixers, and seminars like this one, and learn from people.